So we just heard about the RTEMS operating system, and its use in space was mentioned. And we have we here at Johns Hopkins University have a space program that is anticipating using RTEMS as the operating system. And that is the Solar Probe mission. And as part of the Solar Probe mission, we're going to have two fairly large solid-state recorders with NAND flash, and we're going to be using a file system for the management of those recorders. Now, that means that we want to be able to bring the file system that we have, the flash file system, into RTEMS and treat it as any other file system that might be supported in an operating system. So I'm going to give you a little bit of an overview about the file system, the flash file system. But that's going to be really short because what this really is, what this presentation is, and I hope it'll be helpful, is really sort of a nuts and bolts. This is how I was able to get this file system into RTEMS. So the flash file system, as I said, it's designed for NAND flash. Flash is write once, read many, and you erase by a block, which means you erase a much larger area than what you want to reuse. Because of these characteristics, the optimum performance is writing to the end of files, sort of making a long stretch across the device by continually writing more data to the file. The file systems support seeking inside of a file and rewriting data, but that's not very efficient because of the NAND flash. The file system, this is an open source. It's based on existing open source. The open source is used in the Android operating system, and it's a logging or journaling sort of file system architecture. Our extensions to this so far, we've completely eliminated dynamic memory allocation, so we configure it to the exact size of our device when we want that we're going to be using, and remove the possibility of non-deterministic allocation problems. And we have enhanced support for large disks or large devices by allowing multiple pages per allocation unit in the operating system. The base file system. The base operating system, the base file system uses write of the allocation size, and what we've done is we've allowed write to take place inside the allocation so that we can have a much larger allocation and yet keep read and write sizes managed. So the RTEMS operating system is being used for Solar Probe. Why are we using RTEMS on Solar Probe? Well, the basic reason is that our target processor is the Aeroflex Geissler Leon 3. And RTEMS is given priority over other operating systems supported by Aeroflex Geissler. They put almost all their effort into RTEMS as opposed to VxWorks. And the integration they've done with VxWorks, we've run VxWorks on the Leon, but it's kind of, you call up VxWorks and they don't know exactly what you're talking about because the board support package was not really produced by Wind River. So RTEMS is much more native to the Aeroflex Geissler environment. We felt more secure with going with RTEMS, just basically for that reason. And there may be others. I didn't make the decision, but that's what we kind of say. So the APL flash file system is operating system independent. It has a direct interface. This was inherited from the open source. It's not terribly innovative on our part. And it has a direct interface so that you can use it in a bare C kind of operating environment. And source is provided for integration into the Linux kernel because it comes out of the Linux lineage. And so you can make calls to the direct interface. You can just kind of plug them into whatever the operating system template is, the file system driver template for the target operating system. Now we tried to go a little bit beyond that and tried to make it a little bit more integral to the RTEMS operating system, and I'll show you the theory of operations on that in just a second. So we just heard about RTEMS, so I really don't have to tell you much about that. We are using RTEMS 4.10, which is the Geisler Spark Leon distribution. We are using that because that's what we get from Aeroflex Geisler. There is currently, and Mr. RTEMS, who you just heard, can give you more details about the releases. But RTEMS 4.11, the file system support has been updated and changed. This presentation will cover 4.10. Haven't really looked into 4.11 because we're really focused on the Geisler Spark Leon implementation. However, there is a little get command there that you can use over the web if you can type that many numbers. I can't, but if you're patient, you can get there, and you can, and that gives a fairly good summary of exactly what is in the 4.11 release regarding the changes to the file. So our basic approach here is the way that the RTEMS work, the RTEMS operating system works is that there's a C standard I/O library, and the C standard I/O library makes calls to the RTEMS POSIX I/O interface. And inside of the RTEMS POSIX I/O interface, it makes calls to standard file system driver interface. That's represented by the small box down there. Now what we have, our source code as we developed it, has the APL flash file system direct interface, which mimics the, it basically mimics the POSIX I/O interface. And so what we do is we take that direct interface and we sort of squeeze it down and remove the redundancies that exist in the RTEMS POSIX I/O library that are, that's already, the features that are already there, and make that interface, that direct calling interface, actually conform to the file system library interface that is supported by RTEMS, and then at that point we should be able to fire everything up, and it'll work just like any other file system under RTEMS. And just a note, once again, I'm not going to be focusing on the specifics and the details of our file system. I'm going to be focusing on what you have to do to take any file system and get it integrated into RTEMS. So this is kind of an RTEMS focused presentation. I'm sorry, I'm having a little trouble going. Oh, there we go. So now I'm going to give you a file system overview, and basically what we're going to do is we're just going to walk through how RTEMS starts up a file system and what you have to do to, at the very highest level, to have a file system operating in RTEMS that you yourself develop, a custom file system. So RTEMS is supplied with a basic in-memory file system which serves as the root for mounting additional file systems and devices. Everything goes through the basic in-memory file system. By default, if you don't do anything special, at least in the releases that we have, The RTEMS is configured with a very simple in-memory root file system, which is called mini IMFS. IMFS means in-memory file system. In-memory, the mini IMFS does not support mount points. That is, it doesn't support adding new file systems to RTEMS. So the first thing that you have to do is the RTEMS release has to be configured with IMFS, which is a bit more robust and allows for the mount point. So in order to effect this change, what you need in your build process, either through your make files or your Eclipse setup or however you do this, I actually have a file that I just throw these pounder signs in because it's simpler, of course. Is you have to define a couple of manifest constants. You have to define configure file system IMFS, and that gets rid of, and configure use IMFS as the base file system. And when you do that, magically the mini IMFS goes away, and the IMFS proper comes in, and you can then start integrating custom file systems into the RTEMS operating system. Now, the location of the code for the IMFS and for the other file system code in the RTEMS release directory is under CPU kit, under live FS, under the source directory. And if you're serious about doing this sort of thing, that's probably the first directory you want to go to and start taking a look at the code that's in there, because that will provide you with examples and templates to steal, leverage in your own code. So the RTEMS operating system, when you compile it and link it, the RTEMS file system you define an init task, and as far as I know, you just give this task the name init, and it gets started up. It's sort of like having a main function with your C application. You just call it main, and that's where your program starts. So as part of the initialization, so you can put initializations and task startups in the init task, and as part of this initialization, file systems are registered. And so the very first step that you want to do in integrating a new file system into RTEMS is you want to make a call to RTEMS file system register. You want to give it a name, which is just a simple string. Looks like 6 characters will do. I don't know what the limits are right now. But you give it a name, and you provide it with what is called a mount me handler. And we will talk more about that in the subsequent slide. The mount me handler is the key to to getting it all configured. Now, this is the way I do things. This information, when you do the file system register, the file system is registered in a mount table or in a file system table. And if you want to, you can track down that table and just make the appropriate modifications to it in the original code. Of course, then you have to be careful about subsequent releases. If you get something, if you bring in a subsequent release, your file system might disappear if you replace that code. So, so you might want to be a little careful about that, but it can be done. And but the technique that I have been using is just to register the file system dynamically upon initialization. Trying to move to the next slide. There we go. I hope I didn't go too far. Sorry for mumbling, I just want to make sure that I didn't go too far here. Okay, so we've got it. So now the next point, the next thing that you do is you have to mount your device. So generally speaking, you'll have some sort of a physical device out there. What we have is a flash, very large flash memory system that's on the other end of the space wire cable. But it could be anything, and it could also be a non-device. For instance, it could be an EEPROM file system, which you might handle just a little bit differently from what I'm showing here. But basically, what the next thing you want to do is you want to mount the device. The first thing you want to do is make a directory that will serve as the file system's mount point. So I just, in my test code, I called that recorder 01. And you just do a regular make directory call, just like you would do in any POSIX.io environment. And then that's going to be the directory that your file system magically appears in. Notice that there's kind of a trailing backslash or slash on the file. And according to comments that I've observed in the code, in example code, that trailing backslash is necessary. I don't know if that's true or not. I just did it because it said do it, and it worked. You can experiment with that, or even track down the reason why it may or may not work without that. But that will work. So after you've created the directory, the next thing to do is to mount your device. So this shows mounting a device. I haven't shown the creation of the device, and that is a little bit independent of my talk here. Right now I'm kind of hard coding the device interface, and I have not yet actually created a device as this sort of appears. This is the actual code that I'm using to mount the device. But I really don't, and there is a device there, but I don't have a device driver actually written that is in a dev directory. But this is how you would do it. So you mount, you give it the device name, you give it the mount point, the directory, the recorder. You give it the file system name as you registered it previously. And you give it the options, and the options that I choose are read and write, because I actually want to read and write to this. However, for instance, in boot EEPROM might be read only, so you can specify that here, there also. And a pointer to the file system specific data, I have null here, and that's optional. And that would be a way that you might pass, for instance, an address range into the file system if you were using some sort of if you were trying to write a file system for a double EEPROM rather than a device. So you can put some optional information in there that's specific to your implementation. So after mounting, then you can use the device just by calling the normal POSIX file operations, open, close, read, write, etc. And then when you're all done, you can call the unmount, which just specifies the root directory. And your file system, your custom file system, should do all the nice things that should be done when something is unmounted. You know, storing away the last remnants of files, tidying up, and making sure that everything's correct before shutting down. And then you can, if you want to, you can mount it again and start all over. So now what I'm going to do is, that's kind of the overview. And what I'm going to do now is I'm going to go into the guts of this and try to show you how we actually make that upper level calling work.
Hey, Alan.
So,
Alan.
yes.
You have about
yes.
You have about 5 minutes left. So try to speed up if you can.
Okay, I'll try really hard. The file system, basically the file system on the RTEMS system is a system of handlers. And the handlers each implement a basic function. So you have a table for file level operations, for instance, the mount that we just saw. And you have a table for other operations, the direct file system operations, open, close, read, and write. And at the end of the presentation here, if you access this off of the web or whatever, there are some examples of these tables. Now, since we're time limited or untime limited, I'm going to try to go through the file system level handlers that are most important and most confusing. They're a little confusing, I think, because perhaps because people aren't used to them. But after you get used to them, they don't seem to be all that confusing, at least not to me. So there's two things that you have to get your file system working. There's two things you have to really get down right, and that's the mount me file system handler and the evaluate path and the evaluate for me. So I'm going to go into this. So the mount me, there's a mount file system handler, but that is used when somebody's trying to mount something under your file system. What you need to implement, without exception, is the mount me file system handler. And that's when RTEMS is directed to mount a file system under you. So that's what we're going to focus on right now. So the mount me interface, you are given a mount table entry, which will prove to be useful later on. And you're given some optional data. And where does that data come from? That's the data that was in the mount call that we mentioned before. I'm just using null for this. Now, you're going to have to, because we're time limited, you're going to have to look at the details to the extent of your interest. But everything you need to operate on your file system as a whole is in the mount table entry. And your goal with the mount me handler is to set up that entry table so that in the future, when you're given a call back, you will be able to use that information to implement the functionality that you're doing. So the processing is you use the device name, which is passed in through the mount, to open the device and access any information that you might need from the device. You initialize each of the root file structures based on the information specific to the root node. And then that information, that mount me table structure, that table structure is provided to you for subsequent calls, and you use all that information to implement the functionality that you need. Now, when a high-level caller calls, they provide a path to the file that they want to, and the path evaluation for make handlers, their job is to find that file in your implementation-specific data structures and fill in information that then can be used to do operations on that file, such as open, close, read, and write. How am I doing for time? I have a feeling that maybe I should.
Yeah, you got about 30 seconds left.
I got about 30 seconds. Will that give me time for questions?
Well, yeah, you have your 5 minutes of questions left, so you can.
Oh, okay. So the idea here is that you'll be given a path, and you'll be given the information that you stored for your root node, and then you can use the path information to find whatever it is in your file system represents the file that's indicated by that path. And once you get that path, once you find that file system structure or that data that you need to do further operations on it, you fill in the structure that you were given, and when the file and when the user calls the specific operation, they'll be presented with that information. The one hint that I can give you right here is that if the path does not evaluate to an existing node, be sure to correctly set error number to no-ent. And if you do that, you'll save yourself a lot of time. That's basically the signaling mechanism that RTEMS file system uses to know that it should create the file as opposed to open an existing file. If you do that, it'll work. So I have some complications here and some other tips and hints, and those of you who are interested in that can go to that. And I'm going to cover the eval for make really quick, and then I'll ask for questions. The eval for make is a little bit different. We get a path name, but we don't expect the path to the file named in the path to exist. What we do is we find the root for that, and then we return the file name, and the file system then asks for us to create, using the make node call, asks for us to create that file in that path area. So the idea here is not to find the file, because we know in advance that it doesn't exist. The idea is to find the root directory that the file is to exist in, and return the name, the solitary name stripped of all the path prefix, so that the make node can be called. And the make node handler, you're going to have to take a look at that yourself. And I'm going to go to the summary, and then we'll ask, and then I'll answer any questions. So when the system open procedure calls, it parses the path that is given and finds a mount point, and at that time it calls the path evaluation handler for the file system that it is encountering. Now, if that file doesn't exist, the path evaluation calls the returns no entry in the error number. If no entry is returned and the create option was specified, the open procedure then calls path evaluation for make, and you gets back the directory and the file name. Then it calls make node using the directory and the file name. And then once again it calls the path evaluation handler just to make sure that everything went okay. And then it actually calls the open file handler. And that is going to be in the next section, and we're not going to get to the next section, but you can take a look at that at your leisure. And so when all of this has occurred, the open file handler, a file handle is returned to the application process, and that's what you get back to use in subsequent calls when you open a file and create it. So that wraps up my presentation within the time limit, hopefully. I do more than
1 minute for questions.
Okay, you're in control.
Does anybody have any questions for Alan?
I'll ask him one.
All right, Joel's going.
This is Joel. Can we use your slides and your notes for a how-to?
I don't know if you could hear that. Were you on the mic, Joel?
There's not a mic.
Could you repeat the question?
Joel wants to know if we can use your slides for a how-to.
Yeah. These slides will be posted. It's my understanding that these slides will be posted on the Flight Software Workshop page. And once they're there, you just do what you want with them. Don't ask, don't tell. I mean, they're out there. So you have fun with that. I was kind of hoping that that's where they would end up somewhere in the RTEMS opus of documentation. So.
Yeah, Joel's nodding his head, so I think you're going the right direction.
Okay, good.